The purpose of this video is to cover the content associated with the first three sections of Chapter 8 and to introduce you to the concept of the mole. Once we've been introduced to the concept of the mole, we want to see how it has bearing on our study of composition stoichiometry. The concept of the mole begins with the gentleman you see pictured on the right. That's Amedeo Avogadro. He was an Italian physicist and mathematician. And in 1811, Avogadro hypothesized that equal volumes of gases at the same temperature and pressure would contain equal numbers of molecules. Here's what Avogadro's principle would look like. Here we've got hydrogen gas, and the blue molecules are representative of oxygen gas. Each of these gases is in an identically sized container. We're going to say that these gases are at identical temperatures, and that when measured, we determine that the molecules of each of these gases is exerting an identical pressure on the walls of their container. So in other words, we have all the criteria necessary for Avogadro's principle to be true. We have all of those criteria in place here. Identical volumes, identical temperatures, and identical pressures. And what Avogadro hypothesized was if all of these criteria are met, then the only thing we can conclude from that is that each container must hold an identical number of molecules. And that's what you see here on a very simplistic level. We've got 6 molecules of hydrogen, 6 molecules of oxygen. Avogadro's principle would remain largely unrecognized by the scientific community until the year 1860, when a fellow Italian, the chemist Stanislao Cannizzaro, would use Avogadro's principle to assist him in the determination of relative atomic and molecular masses. If I told you that because I'm a warm and fuzzy, hopeless romantic who likes long walks along the beach, stuffed animals, and chick flicks, that because of that I had ordered a dozen long-stem red roses for my wife, you would know that I had in fact ordered 12 long-stem red roses for my wife. And that's because you are comfortable with the fact that the word dozen has a numerical value associated with it, and that's 12. Well, the quantity dozen works well for very large objects. In chemistry, we deal with much smaller objects, things like atoms and molecules, and so consequently we use a unit known as the mole. Now, a mole is technically defined, as you see, as the number of carbon atoms in 12.01 grams of carbon. That doesn't mean much to us. What you do need to be familiar with is that the numerical value associated with this word, the mole, is 6.02 times 10 to the 23rd. And it's a gargantuan number. And this term, the mole, has a synonym. A mole is the same thing as Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23rd. Now, I mentioned that this is a huge number. Notice, if I had Avogadro's number, 6.02 times 10 to the 23rd, if I had that many aluminum soft drink cans, they would cover the surface of the entire Earth to a depth of over 200 miles. If I simply had Avogadro's number of unpopped popcorn kernels, and I simply spread them across the United States of America, it would still cover the landmass to a depth of over 9 miles. By the same token, if I was somehow able of counting, in this case atoms, at the rate of 10 million per second, which we know I can't do, but if I could somehow count from 1 to 10 million in a single second, it would still take me about 2 billion years to count to Avogadro's number. Couple of more examples. If everybody on planet Earth, right here, right now, 6 billion people, tried to count collectively Avogadro's number of objects, it would still take us over 3 million years to accomplish this. And perhaps my favorite one is this. Let's suppose that at the time the Earth formed, according to evolutionary theory, if it formed 4.5 billion years ago, and I was given a mole of dollar bills at the time the Earth formed, if I spent $1,000,000 a second over that 4.5 billion year span, right now I'd still have about 3/4 of the money remaining, and it would take me another 15.5 billion years to spend it all. So hopefully at this juncture you're convinced the mole, Avogadro's number, 6.02 times 10 to the 23rd, is a phenomenally large number. Well, a little bit of history here. Avogadro never knew about the concept of what we are referring to as the mole. He died in 1856, and the term mole didn't really come into use until about 1900, when it was introduced by the German chemist Wilhelm Ostwald. He never knew of the number 6.02 times 10 to the 23rd that bears his name. And what I want you to be sure of is, even though 6.02 times 10 to the 23rd is known as Avogadro's number, he had nothing to do with the determination of the number. It's named that in his honor because ultimately Avogadro's principle played a role in its determination. One of the great things about the concept of the mole is that it allows us to count atoms and molecules by weighing. Let me give you a macroscopic example of what I'm talking about before we go back to the submicroscopic world of atoms and molecules. You see the stack of pennies there on the right? Suppose I said, I want to know how many pennies there are in that stack, and I gave you that assignment. One of the ways you could go about doing that would be to simply count them one by one. It would be slow, and it would certainly be very tedious and mind-numbing. You're much smarter than that, though. You come back to me and you say, give me a balance. So I give you a balance, you place a single penny on that balance. You determine that its mass is 2.5 grams. You then take and place the entire stack of pennies on that same balance. You determine that the total mass is 2,500 grams. Then, utilizing a little bit of mathematics, 2,500 grams divided by 2.5 grams per penny, and you determine rather quickly that there are 1,000 pennies present. This works real well in this example of pennies in the macroscopic world. Atoms and molecules are much smaller than pennies. And so consequently, even an extremely small chemical sample contains a huge number of atoms or molecules. And so counting atoms and molecules is not possible. So the concept of the mole is going to allow us to bridge the gap between the submicroscopic world of atoms and molecules and the macroscopic world in which we live. Here's what I mean about bridging the gap between the submicroscopic world of atoms and molecules and the macroscopic world in which we live. If you look at hydrogen, its average atomic mass is 1.00794 AMUs. We're going to round that off to its mass number. We're going to say 1 AMU. An individual atom of hydrogen has a mass of 1 AMU. Now that's a mass way too small for us to deal with. However, if I have a mole of hydrogen atoms, if I have Avogadro's number of hydrogen atoms. If I have 6.02 times 10 to the 23rd hydrogen atoms, I have 1 gram of hydrogen. And believe me, I am capable of going somewhere and measuring out 1 gram of a substance. That's a quantity that exists in the macroscopic world. Need another example? Let's go over here to aluminum. Aluminum's average atomic mass is 26.981539 AMUs. We're going to round that off to a mass number of 27. The mass of a single aluminum atom is 27 AMUs. Far too small for us to deal with. Well, if I have Avogadro's number of aluminum atoms, or if I have a mole of aluminum atoms, or if I say it this way, I have 6.02 times 10 to the 23rd aluminum atoms, then it would have a mass of 27 grams. And again, that's a quantity that I could work with in a macroscopic setting like our lab. Copper's average atomic mass, 63.546 AMUs. Remember that copper's one of those atoms that we're not going to round off to the nearest whole number, and we're going to say that copper's mass number is 63.5 AMUs. So a single atom of copper would have as its mass 63.5 AMUs. If I have a mole, if I have Avogadro's number, if I have 6.02 times 10 to the 23rd copper atoms, I have 63.5 grams of copper. And hopefully you see that really all I'm doing is changing the unit associated with the mass number from AMUs, atomic mass units, to grams. And that will work for every atom on the periodic table. It will ultimately work for every molecule with which I work. More about that later. Now, the mole is extremely important to chemistry, and we also like to have our fun with it. And that's what these next couple of slides are about. You'll notice on the left here I've got Larry, Mole, and Curly, and these guys are capable of bringing us 6.02 times 10 to the 23rd laughs. The Avogadro volcano spews out molten lava. My favorite one here on the left is guacamole, and you'll need exactly 6.02 times 10 to the 23rd avocados for that. I've even discovered that there's Avocado's number guacamole and an Avogadro's number restaurant in Fort Collins, Colorado. Given you the phone number there in case you wish to make your reservations. And National Mole Day is celebrated by chemistry teachers throughout the country on October 23rd. That's the 10th month, that's the 23rd day, and it's typically celebrated at 6:02 in the AM. And if you put that together, you can see that is 6.02 times 10 to the 23rd. Here's some of the merchandise that you can purchase for that day. And I will tell you the reason that we typically do not celebrate it around here is because, quite honestly, we haven't yet covered the concept of the mole, and so it really wouldn't make a great deal of sense in a pre-AP chemistry course to celebrate it. The last thing that you'll see here, this was, I believe this is my costume at the most recent New Year's Eve party. I did go as a mole, and that brings our introduction to the mole to a conclusion, and with the next video we'll begin using the concept of the mole to make composition stoichiometric calculations.